In a previous tutorial, we talked about inferences on the square of opposition. Now, these are immediate inferences, which means that the truth of a categorical proposition is all we need to draw another inference about the relation between the two terms in that categorical proposition. Today, we want to look at a different kind of immediate inference, this time inferences by mechanical transformation. In this case, what we have is three operations, three sort of mechanical operations that we do to categorical propositions to essentially turn them into a slightly different form. And then these forms are either valid or invalid depending upon whether the proposition implies a true proposition when it's transformed using this mechanical operation. Now that's all pretty opaque, so let's jump right on to the first example, and I think this will make a little bit more sense. So this is a standard form for an I proposition. The I is some S is P. The operation that we want to look at is conversion. So what do we do to perform this operation? Essentially, we swap the terms. So notice we have S in the subject position, P in the predicate position in the premise. That's the starting point. But when we go to the conclusion, P moves up to the subject position and S moves back to the predicate position. Now, notice one thing about this. There's nothing magical about S and P. In other words, S just stands for some category that happens to be in the subject position in this proposition, but it could be anywhere. It can be in the predicate position in a different proposition if we put it there, basically, right? And conversion puts it there. So if we take the I, some S is P, and we convert the I, meaning apply the operation conversion, we end up with the proposition some P is S. Now notice you can do this with any categorical proposition. So we have four types. You can apply this transformation process to any of them. So for instance, we could start with no S is P, and what we would do is swap the subject and predicate terms, keep everything else the same, right? So the quantity quality will stay the same, so it's going to be universal negative. We're going to have P up front in the subject position. Our copulative verb stays the same, and we have S in the predicate position. So here we go. We've got an E proposition as our premise. No S is P. Applying conversion, we end up with the proposition no P is S, just by swapping the subject and predicate terms. It's important to notice that this mechanical transformation leaves a lot of things unaffected. So for instance, the E is universal. The result is also an E. Notice it's an E in terms of its form, universal negative. So the conclusion is universal. This starting premise is E. That means that it's negative. The conclusion is also negative. So it's important to see that we retain a lot of the characteristics, even though we're making a change in the operation of conversion. So let's look at one more example of the mechanical operation itself. Let's look at A. So the starting premise would be all S is P, and the conclusion would keep universal affirmative, so we're keeping all of those parts. We move P up to the front, we move S to the back, and so by conversion, we get the conclusion, all P is S. Okay, now, there's another question to ask, which is whether these inferences are valid. And by validity, we mean if the premise was true, the conclusion cannot be false. That's a different question. I want to save that for a moment. We'll come back to that, because obviously an inference is only as good as it guarantees the truth of the inference that we're drawing, right? So we're really going to be concerned about the valid inferences, and not all of the mechanical transformations turn out to be valid. But first, let's introduce all the transformations, and then we'll come back to the question of validity. All right, so let's move on now to the other two on the list. The other two involve a concept that is pretty easy to explain using a bit of basic set theory. And this is the notion of a complement. So let's say we have a set, and the set we've identified as S. So here's the set. We could think of this set as existing in a universe of items. So for instance, there's a set of, for instance, dogs. The set of dogs exists in a universe of things that include dogs, but also include other things like goats and pens and keyboards and things, right? So if you think about this set S in relation to the whole universe, then you could basically divide everything there is into two sets. There's the set of everything that's inside S. In other words, that's the set of all the S's there are. But there's the set of everything that is not inside S. So what is that set? Well, we could conveniently label that set non-S. So think about it. Everything that is an S belongs in the S circle. Everything that is not an S is outside the S circle in the universe. And so we have two sets, S and non-S. The relationship between them is not quite like what we think of when we say opposites, right? Sometimes opposites are complements, but sometimes they're not. So for instance, if I were to say to you, what is the opposite of an avocado? I mean, it's kind of hard to, you have to fill in some more of that question in order to answer it, right? But with respect to this notion of complements, it's easy to identify the complement of the set of avocados because that is the set of non-avocados. So now we have two sets. We have one set that contains all the avocados there are, and another set that contains all the non-avocados there are. And so what is the implication here? If you take these two sets, like you take the set S and union, in other words, put them together with the set of non-S, what do you get? You get the whole universe. Okay, so back to our avocados. If you take the set that includes all the avocados there are, and you put them together with the set of all non-avocados, you get everything there is. So that's the relationship between complements. And the way we signify that in categorical logic is this little complement operator on the front side of the term. So we have S and non-S. If we had a category P, we could have P and non-P. If we had a category C, we would have C and non-C. And that's how we indicate that these two sets are complements of each other. Another interesting thing to notice about this is it's not the same relationship as negation. Negation in categorical logic is about excluding something from a set. So for instance, if I said that something is not an avocado, that's excluding something, some particular thing from the set of avocados. The set of non-avocados is just a name for a set that happens to have a certain relation with avocados. I think that'll become a little clearer as we work through some of the mechanical transformations on our types of propositions. For now, though, the really important thing is this relation right here. So we have a set or a category or a term. We have its complement, which we signify by attaching the operator non on the front of it. And the union of these two complementary sets is everything there is. Okay, excellent. Now let's go back to this, and we'll look at the mechanical transformation obversion. Okay, so this is a good example of what happens in obversion. So the first thing to notice is, what do we keep? We keep the quantity. So we start with the universal and end with the universal. We keep the is intact, right? So that's our copulative verb. But look what does change. We've changed from affirmative in the premise to negative in the conclusion. So we're going to change the quality from whatever it is to the other quality. And remember, there are only two, affirmative and negative. So If the premise is negative, we switch to affirmative. And if the premise is affirmative, as it is here, then we switch to negative, as it is in the conclusion. But the other thing we do is we take whatever is in the predicate position. So the predicate of the premise categorical proposition, and we take the complement of that predicate. So that's the operation. Switch the quality and take the complement of the predicate. Otherwise, everything stays the same. Notice, S stays the subject in the conclusion. The complement of P becomes the predicate. So we're not changing anything else except these two things. Change the quality and take the complement of the predicate. So we start with the premise, all S is P, and we end with the conclusion, no S is non-P. Well, let's take another example. This time let's use O as our starting point. So we have some S is not P. Okay, and so to do the mechanical transformation, we're going to change from the quality that's in the premise, that's negative, to affirmative. So we're going to drop out the not. We're going to keep the same quantity, so we're going to use some because it's particular. We're going to keep S where it is, and we're going to take the complement of the predicate. So the result of this proposition, of this mechanical transformation on an O proposition, is actually an I proposition. And that makes sense because we start with an O, which is particular negative, and the only thing we're changing is the quality. So we've got an affirmative this time that's still particular in quantity, right? The difference, of course, is that instead of P as the predicate, we end up with non-P. Now think about this for a minute. Some S is not P is a claim about excluding something, right? In other words, there's at least one S that's excluded from the set P. But that's not what the conclusion claims. The conclusion claims a different thing. Now, it is a nuance, but it is a different claim. And that claim is that there's at least one S that is inside a set. And what set is it inside? It's in the set non-P. So if you want to think about this in terms of the complement idea that we had in the previous slide, think about it like this. So here we have S and P. The diagram of the premise is some S is not P, says that there's at least one S outside of P, right? And if you think about it in terms of the conclusion, the set of non-P is everything outside the P circle in this whole universe. So what this proposition is claiming is that there's at least one S, here it is, that is inside a specific set, namely non-P. It's just that non-P happens to be the big set of everything that's outside the P circle. But it's still a set. So we have changed from an exclusion relation to an inclusion relation, but what the index is, the sum S is included in, is a different set, namely the complement of the original predicate. Okay, and again, you can apply this mechanical operation to any of the four types. So you can play with this in your head. So for instance, if we start with an E, that'll give us no S is P as the starting point. We're going to change the quality, so it's going to become affirmative. And we're going to take the complement of the predicate term, and so we're going to end up with all S is non-P. So it follows this pattern every time. All right, one more mechanical operation that we want to look at is called contraposition. Now, in contraposition, we're going to keep everything the same, except we're going to swap the complements of the subject and predicate of the original proposition. So look at this. We start with an A type. The A is what? Universal affirmative. So that's an A. And we're going to end with an A because we haven't changed anything about the quality or quantity. What we are going to change, though, is we're going to take the subject term of the premise, put it as the predicate, and take the complement. We're going to take the predicate term of the premise, move it to the subject, and take the complement. So we start with all S is P, and we end with all non-P is non-S. And again, we can do this to any of the propositions. So let's do the O. That gives us some S is not P. Okay, and then we're going to keep everything the same. Some stays the same. Is negation stays the same. So we've got particular negative. The difference is we're going to take the predicate and move it to the subject position and take the complement. We're going to take the complement of the subject term and move it to the predicate position. And that is the result of applying contraposition. So what I would ask you to do is think about these mechanical operations and sort of rehearse or practice them in your head or written down until you become familiar with these patterns. These patterns don't change. What will change, of course, is we want to determine whether these inferences are valid, and I will talk about the validity of these inferences by transformation in the next tutorial.